All right, so to finish up our coverage of binary search trees, we'll discuss the final operation today. That is deleting a node from a binary search tree. Because we saved this for last because it's it's the most complicated. But the first step in this is just like the other two operations of inserting or searching for something. You got to find it first, right? So first of all, you search for the node containing the key you want to delete, right? Because if it doesn't exist, of course, there's no operation, or you can throw an exception or whatever, right? If it does not exist, no op, or throw an exception, etc., right? Otherwise, it does exist, and so we need to delete this node now. We're going to split this up in a couple of cases. The first case is going to be the easiest case. Let's come over here to our tree that we've been working with, and let's suppose that we want to delete 12, right? Now again, we always start at the root, and then we traverse left or right depending on the value of it. And so we'll come down here, come down here, come down here if we find it right there. Now, how do we delete that? Well, all we have to do is sever this connection. Once we've severed that connection, then this effectively goes away, right? So in other words, if there are no children, then all we have to do is make sure that the parent-child connection is cut or severed, right? And all that we're going to do for that is that the 15 here, it's left child, we'll set that equal to null. And if there's a programming language like, say, C or C++, we'd also have to clean up this node and set the parent reference of the child to null, but we're not going to have to do that because it's Java. So all I'm going to do is make sure that the parent's left child, I'll set that equal to null, and that effectively gets rid of that that node right there. All right, so let's go ahead and implement that first case. All right, so let's come over here, and I'll go ahead and do it at the bottom here. Public t delete, right? And we'll go ahead and take t sub x here, right? Now I'm going to return this t here because once we've deleted the node, I will take the contents of that node and actually return it. So deletes the node containing the key x, the value x, and returns it, right? So that's why we have this return type here, okay? So the first step, as I said, step 1, find it. Right. Well, we've already implemented that. In fact, we've implemented it twice now. Once when we were doing a search method, we went left or right, starting at the root, we went left or right until we found what we were looking for, or we fell off the edge of the tree and we returned null. We did it a second time, but a little bit more sophisticated when we were doing an add method, because we kept track of both a previous and a current. If we ever found that the current already contained that element x, then it was a no operation and we returned. But otherwise, we kept track of the current and the previous because what we eventually wanted to do is find where it should belong, right? So we wanted to fall off the edge of the tree because if we were inserting, say, 13 over here, right? What we wanted to do is we wanted to find 12 so that we can make 13 its right child. So we were keeping track of a previous and a current until the current fell off the edge, and then we used previous to set the new child. Right? We're going to do the same thing here, or we're going to do something similar, but I'm thinking I've repeated myself a lot here. Right? I already have this same basic while loop in two different locations. Ultimately, what we're going to do is we're going to take that while loop and put it into another function. So actually, let's go ahead and do that before as a first step here, because I want to clean this up a little bit. All right, so let's below this search here, let's go ahead and create a public. Actually, no, I'm going to make it. I'll make it public at first. Public binary tree node t. All right, and I'll just have find, and I'll say x. All right, and what I'm going to do is I'm going to take all of this logic here for this search, right, and I'm going to move it down here. Now, why did I make it into a find? In fact, I'll rename this to find node. Why am I trying to find the node? because that gives me more information, right? If I were just trying to find 12, right, then that would be done. I would be done here and I'd only have 12, the actual value here. What I want is the actual node, because potentially I want to go back to the parent, I want to go to the left child, I want to go to the right child, right? So what I'm going to do is I'm going to refactor this so that I'm returning the node instead. And here I will return null if it's not found. Otherwise, instead of returning the get element, I'll return current. And that's it. Oh, I guess the key, it's not the key, but it's X. X and X. There. Okay. All right. Now, because I put that into another function up here, that really simplifies things up here. All I have to do is call that function, say this dot find node of X, right? And I don't need to repeat myself, okay? Once you've found that node, right, key, there we go, right? Then you can go ahead and return the value stored in that node. But you do need to be careful because you need to check for null pointers. Because remember what happens with an unsuccessful search, this current node here, or I'll just call it node now, right? That will end up being null. So if node is not equal to null, what I will do is I will say node dot get element, and that's what I end up returning. Right? Otherwise, return. There we go. Right? Otherwise, I will return null. Right? Now that greatly simplified this function, but that just means that I'm putting all the actual logic over here into this find node class. Now, why does that help me? Well, what I could do is I could come up here to the, to the, what was it called? To the add method. And I don't have to repeat myself here, right, with this while loop here. Right? The problem is that I kind of do have to repeat myself in that I have a slightly different behavior. I'm keeping track of the previous and I'm keeping track of the current. That's okay. Why don't we just design that into another function, right? Before we do that though, is this a good idea? This public here. Should I be allowing the outside world access to my binary tree nodes? We called that a leaky abstraction, right? So I'm going to go ahead and make that into a private because I still want the functionality, but I want the class itself to use it. I don't want anybody outside of the class to use it, okay? All right, if you actually want the node that stores that one key, then that's what you would call. But what I actually want is the parent. Find node parent, right? There we go. And that will give me both information, right? It'll give me the parent. I have both options, basically. If I'm searching for a particular node, I want to find that node. Otherwise, I want to find the parent because I know that that node doesn't exist, right? For example, if I'm inserting 13 here, I would have to find this parent here so that I can insert it as the right child of 12, right? So let me go ahead and implement this now by stealing this code from up here, right? Let's see. All this new, yeah, because we're not going to insert anything. I just need all of this stuff here. There we go. And there. I'm going to take that and move it down here to find the node parent. All right. Get rid of all of that. And by the way, I can't just find the node and then go up to the parent because the node might not exist. Okay. And let's modify it because we need to actually return the result here. All right. So if it's already X is already in the tree, that means we found it, and so we need to return the parent. Return previous. All right. There we go. Otherwise, I go left. Otherwise, I go right. When I've broken out of this while loop right here, right, then that means that I've fallen off the edge of the tree as far as the current node goes, meaning that I return the previous. Return previous. Right, there we go. That will give me the parent node. Okay. Now that I made this a little bit of investment up here, and I can go back and refactor a couple things to cut down on my code. Basically, what I want to do is I want to use that to find the parent, right? So I'm going to call that this dot find parent node of X, right? And let me go ahead and give it a proper name, binary tree node of elements of type T, parent. There we go. There we go. And so I've not found the node, but I have found the parent of the node, okay? Why do I want to find the parent? Because again, if I'm deleting 12 here, right, I want to find 15 so that I can sever that connection right there, okay? All right. So it also might not exist. So you could, what I'll do is I'll put in a to-do here. To-do, verify that X exists. If not, then return, right? The return null in this case, okay? Actually, I could do that right here, right? I could say, if parent dot get left child dot get element, right, is less than, and I would have to use my comparator here, X, then I can go ahead and do that. I don't want to really do that. I'll just leave that as a to-do up there for an exercise for you, all right? Otherwise, I've found the parent, all right? Now, if the, actually, I do want it. Yeah, let's go ahead and do it. Okay, yeah, let's do it up here. Let's go ahead and find the node here. Node, there we go. I can make this a little bit easier. And I don't want to find the parent, I actually want to find the node containing X. And now I can check if that node is null. If the node is null, then that means that you're trying to delete something that doesn't exist. For example, over here, you're trying to delete 42. What should happen? We could throw an exception, we could return false, we could do whatever we want. In this case, I'm going to actually just return null because it doesn't exist. Right? And I have to return something there. I'm not going to throw an exception. Right? Now that I've got that node, right, step one, find it, I'll move that up there. There we go. Right? Then I can go ahead and get the parent really, really easily here. All I have to do is say node.getParent. And I can replace this code right here. This, I don't have to find the parent node, but this dot, or not this dot, but node dot get parent. There we go. All right. Okay. And we're probably going to have some corner cases later on. But otherwise, let's go ahead and come over here and remind ourselves that once when we're deleting something with no children here, right, then we just have to sever the connection from the parent. So I'm going to check for that, right? If this node dot is leaf, right? Then all I have to do is there are no children. Otherwise, it's going to be a little bit more complicated. So let's just go ahead and sever the parent-child relation. And how do I do that? Well, I've got the parent, so parent dot set one of its children, child, and I'll leave it like that to null. I didn't want that, right? I just wanted child, right? Which child here? Right. So which child are we going to do? Well, if it's a situation where I'm trying to delete 12 here, then I would delete 15's left child. But what if it was different? What if it was, let's see, what if it was 28 here, right? That means that I would have gotten a parent of 24 and I would have had to delete the parent's right child. So what I have to do is I have to determine which one is the case, right? And so I have to ask myself, and I'll put it in the code in the comments here. Let's go ahead and get rid of this for a second. If the node is the parent's left child, then delete the left child. Right? Otherwise, else if the node is the parent's right child, then I will delete the right child. Okay. All right, so let's go ahead and translate that into code. How do I say if the node is the parent's left child? Right? So if parent.getLeftChild, right, is equal to, and I'll put a question mark there, to x, actually it's element.getElement, there we go, is equal to x, then I know that it was a left child. Right? And so to delete the left child, it would be parent.setLeftChild equal to null. Right? And then I have an else here. Do I actually have to check for left or right? There is no other option here. So all I have to do is delete the right child. And so parent.set right child, right child to null. Okay? And there's the logic for doing that. Now the problem up here is, can I do this equals equals here? If it were integers, yes. But what is equals equals actually doing? It is comparing memory addresses. For example, strings. Hello and hello. If they're completely different strings stored in two different memory locations, you can't do that. And so how were we doing it yesterday? We were handing that responsibility off to the comparator, right? And we were asking, is it left or is it right? Okay. And I'll go ahead and add that right here. Right? So this .cmp compare my element with x. There we go. And if that is less than 0, then you do one thing, otherwise you do the other thing. Now let's make sure, we made a mistake last time on and switched those around, so let's make sure that we're not making that same mistake here. So I'm asking the parent, if your left child, if that element is less than x, that means that, so I should probably go the other direction there, I think, right? Let's go ahead and put in actual values here. What if it's integers? The left child is, say, 12. And actually, no, what do I want? I want them to be equal, right? Is the left child the thing that we're looking for or not? There we go. All right, so one compiler error, what's wrong? Oh, okay. So I would need to save it off. At the end, what am I going to return? Return node.getElement. There we go. Otherwise, I would have returned null already. Now it's compiling. All right, let's go ahead and test this out. And I'm going to test it out visually. We're going to use the same binary search tree that we've been working with up to this point. BST dot remove, or did I call it delete? Delete 12, because that's the one that we were looking at. Let's also, at the same time, make sure that we're deleting the other side. Remember that if we delete 28, that would be deleting the right child of some parent. And so let's go ahead and delete 28 as well. And we'll do it in 2 phases here so that we end up getting this printed out. I think actually this is probably going to crash, and we're going to discover why here in a second. It's going to end up with a null pointer exception. Oh, no? Okay. All right, fine. Let's go ahead and test it out. So I've got my visualization tool up here. It's just an overleaf. I'm going to go ahead and cut and paste that output and recompile it. Remember that we're deleting 12, so 12 should be gone. And then we're deleting 28, and 28 should be gone. 12 is now gone in that second phase. And if 28 is about to be deleted, and it didn't work. Right? Why? Let's come back over here. And there. All right. So if it's a left child, 12, then it got successfully deleted. Otherwise, we set the right child to null here. What's going on? Why is it not working? Yeah.
I think you tried to delete 18 on the
Oh, the wrong number?
Yes.
Oh, 18th. Duh. Thank you. All right. So this should result in a null pointer exception intentionally. All right. Now let's find out if it does. Come on. Yep, there we go. All right. Let's come back over here and discover why now. Right. So what went wrong was, well, what went right was that we deleted 12 and that worked. All right. But now think about this. The parent here is 24, and we does have, and its right child is over here. Okay. So let's come over here and ask ourselves, why are we getting a null pointer exception up here when this is false? In fact, that's where we are getting it. On line 141, right? So what we're doing is we're trying to find the left child. Is there a left child of 24? No, it's null. So when we go over here to try to get its element, what's going to end up happening? The left child here ends up being null, and it is in fact that get element, because the return value of get child is null. There is no left child there. So I need to be a little bit more protective over here. If you remember, this is called short circuiting, where you put in a null pointer check and then you have an and with it. So if this dot, sorry, not this, but parent dot has left child, and, there we go, and it's equal to the thing that we're looking for, then go ahead and delete the left child. We don't have to check for a right child, by the way, because otherwise we wouldn't have been at this place in the code at all. We would have returned already because the node doesn't exist. All right? So I'm being a little bit more defensive here, and then remember that this is called short circuiting, because if the first one is false, right, then the second one is never even executed. And now this should run, and it should be correct. Let's go ahead and copy and paste over here. So, where's my first one? Yep, there we go. All right, and paste, and let's recompile. And remember that this code is in Lab 15 if you want it, and you can generate these things as well to visually debug stuff. All right, so it deleted 12 successfully, and did it delete 28 successfully? Yes, it did. All right. So there's our first case. If it has no children, then just go ahead and cut it out like you normally would with a linked list. You do have to be careful though, because it is are you trying to cut out the left child or are you trying to cut out the right child? Okay. All right, let's take a look at another example, or another case here. What if I wanted to delete 49? Right? Now, of course, again, you'd have to find it, and so you find it right here, and that's what we want to delete, 49. Right? Now, it has a child, but it only has one child. Right? It doesn't have a right child, and it does have a left child here, and more to the fact that it could actually have an entire tree hanging off of it at that point. So what I want you to do is I just want you to focus in on, this area right here. All right? And if I were to stretch it out, what does it actually look like to you? Node connected to a node, connected to the node. And what we want to do is we want to remove this middle node. Hopefully that looks familiar. What is that? It's a linked list, and that's how we deleted from a linked list. So if there's one child, then all we have to do is remove by promoting up that child. Okay? And what I mean by that is all we're going to do is make the new right child of 45 into 48. Right? Circumventing these two references here. Also, we do need to make sure that 48's parent is now referring back up to 45. Because this is kind of like a doubly linked list where you can go next, but you can also go previous. You can go down to your child, or you can come back up to the parent from the child. Right? Okay, so that's our second case here. Let me go ahead and put an else statement here, else if. Right? And let's go ahead and promote this up, and this is going to be node dot has one child, right? Is only child. And then we'll go ahead and fix that here in a second. All right? But otherwise, that's going to be our second case here. And I will put that behind an else if. There. Now, how do I tell if a node is an only child? Well, can tell if, are you a left child? Are you a right child? Are you a root? Are you a leaf? I did a whole bunch of stuff, but I never did the number of children. So now let's go ahead and do that. Let's go back over to this class. And I've got, all these nice convenient methods of that it has a parent, it has a left child, has a right child, is leaf, is root. Let's go ahead and add in a only child, int num children, right? Okay. And so let's go ahead and create a result. Initially, that result is going to be 0, and I'll return the result. And now we just need to check for children. If this dot has left child, right, then I will say result plus plus, no space. Right? And independently, if this dot has right child, then I will increment the counter again, result plus plus. Right? Now, if the number of children is 1, then I know that you're an only child, and I know how to delete you now by changing the parent's reference and then changing your reference as well, or the child's reference as well. So if node dot number of children is equal to 1, then it's an only child, right? Child. That is, we need to promote up the left or the right child, depending on which one exists. Okay? Dot, dot, dot. So we'll just have another condition here, and we'll clean this up later on. This is kind of, this is too much nesting for me at this point. We've got an if within an if. So if node dot has left child, then I will promote up the left child, right? Otherwise, else, if node, and I don't need an if here, dot has right child, then I will promote the right child. All right, so let's start cleaning this up a little bit. Do I really need this, this if condition right here? Right. On line 138, I know that you only have one child. You either have to have a left child or a right child. I know that as of line 143 that you have no left child. Otherwise, we would have executed this code right here. Right? So do I really need this check? No. So let's clean that up. Right? All right, so promote up the left child or promote up the right child. What does promote up the left child mean? Right? Well, it means that I'm going to set, what would it be? Parent dot set left or, come on, I don't want you to code completing. Set left or right child to the left child, right? And what does that mean? That's left, right, left, right. What's going on here, right? Well, remember that we don't know what the relationship between 49 and its parent is. 49 is the right child of 45. So we want to go up to the parent and we want to set its right child down to 48, which is the left child of 49. That's not always going to be the case. What if it were reversed? What if it looked something like this instead? And that was left, right, so that was right, left, so let's go left, right. There we go. And what we'd have to do is we'd have to say, okay, well, I'm going to delete you. So you are the left child of your parent. So I need to set the left child of the parent to the right child of this guy right here. In fact, there's other cases. What if it's like this, right? This one is you are the left child of your parent and you have a left child. So I need to set the left child of the parent to the left child of you, right? So there are lots of cases here that you'd have to go through. I think I've simplified it by getting that getting the child already, but let's go ahead and do it. So I need to set the left child or the right child means I need another check. If the parent's left, and now it would be left child here, right? Left child is equal to the node, then I need to parent.set left child to node.get left child. There we go. Otherwise, else if parent's right child is equal to the node, then I would set the parent.set right child to node.get left child. There we go. And that's what I mean by these four different cases here. This is case one, that we're going to replace it with the left child. Case two is going to be replacing it with the right child. But we need to know, with respect to the parent, am I a left child or a right child? Right? Because I need to set the parent's node that way. How am I going to do this? Parent's left child is equal to the node. Right? Well, let's get the parent's left child first. Parent dot get left child, right? Dot get element. Now, if that's equal to the node, well, I don't need the node anymore, right? I just need x. Right? If that's equal to x, then I know that you were a left child. Come on. But I can't just use equals equals. What would I use? Else. Else if. I'll leave it like that for a second. There we go. That's a little bit better. I need to use this.cmp.compare. Parent dot. There. Okay? And if that's equal to x, means that the comparator would return 0. Okay? Else if, now again, do I need this if? You're either a left child or a right child, right? So I can go ahead and get rid of that. Okay? And make sure that my parentheses and everything is balanced. What's wrong with you? 1, 2. Do I not have enough parentheses up here? Oh, what is wrong? It's not closed?
Yeah.
All right, well, let's add one more. This dot, no, it looks closed to me.
Well, yeah, the bracket is
Oh, thank you. I don't have a bracket in front of the else. There. That's what, pseudocode, right? Anyway, this is basically going to be repeated, but instead of promoting up the left child, what am I going to promote up? The right child, right? So, come on. And I will change these two left childs here to right child and right child. Get right. There we go. All right. Once again, let's go ahead and test this because it is complicated. I mean, it's not that complicated once you break it down, but there are 4 cases that you have to deal with. One that's skewed to the left, one that's skewed to the right, one that zigzaggy left and right, left, right, or right, left. So let's come over here to demo and let's go ahead and clear these out. All right. Let's find some candidates for deleting here. Let's see. 45 would be a good candidate because that will be a skewed to the right, then to the left. Right? What else would be a good candidate? 60, because that is skewed to the right, and then you also have, well, no, it's skewed right there. So let's do 45 and 60, and then we can test a couple of others. 24 would be another one. So 24, 45, and 60. Let's do all 3 of them. 24, and let's go ahead and cut and paste. 45 and 60. 45 and 60. There we go. Hopefully it works because I don't want to debug this. All right. Let's come back over here to our visualization tool, overleaf, and let's go ahead and get rid of all of that. I'll leave the original intact, and let's go ahead and recompile this. And once again, remember that we are deleting 24 first, so let's go ahead and scroll over. There's 24, all right? Ah, come on. I hit back too far. Come on. Load. All right, so we're deleting 24 first, and that means that 28 got promoted up. Looks like it worked. We are deleting 45 next, so 49 should be promoted up. Don't lose 48 there. Right? 49 should be promoted up, and 48 is there. Right? Great. Right? And finally, we're deleting 60. So 60 should end up being gone, and then 90 will be the new subtree on at the right of 50. That looks like it works to me. Right? Cool. Now, throughout that process, I was never resetting the parent. That's okay. We can go back and do that. I'll leave that as an exercise for you. But what I want to do is I want to do the last case here because it's the most complicated. Well, yeah, it's kind of the most complicated. Right? All right. So let's actually delete, I don't know, 40. All right. So let's go ahead and delete 40 right here. All right. Well, now it has 2 children. So the first case was no children at all. That was easy. The second case was a little bit harder when you had 1 child, but you could always promote that child up. Right? Now in this case, you could promote 45 up. What would that look like? 45 is now here, 49 is over here, and 48 is over here. But there's no guarantee that that would have worked because what if I had inserted, say, 44 over here? Could I have simply just promoted up 45 here? If I did that, then 45 is here, 20 is still its left child. We now have a 3rd child here, 44 and, what would it be? 44 and 49. 20, 44, and 49, with 45 being up here. And that doesn't look like a binary search tree to me. That's a ternary tree, and you can do ternary trees, but we're not doing ternary trees right now. So you can't simply just promote up the left or the right child, right? Because there could end up being 3 children at that point. What I want you to do is I want you to focus on this subtree right here, okay? Fine, circle it instead. Now, what I want to do is I want to go ahead and remove 40. Right? In other words, I'm going to go ahead and fill that in, and now there's a gap. Right? Is there something over here in this group of nodes that I could promote up here to make sure that the binary search tree property still held? In other words, everything over here was still less than whatever I put here, and everything over here was still greater than whatever I put here. What could I put here? Could I put 10 here? No, because 20 is greater than 10, so that violates. Could I put 15 over here? No, because again, 20 is there. Well, could I put 20 up there? No, because 24 is still greater, and it should belong over here now. What is the one thing that I could put here to ensure that everything else would be less than it? In this case, it would be 28. Too thick. 28. Right? Now, how did I know that? What is the property of 28 with respect to all these nodes over here that means that I could promote it up? It's the largest one. It's the maximum one. So what we're going to do is we're going to go to the left, go to the left tree. And by the way, we could have gone to the right tree. Among the right tree, what could I promote up here? The least thing, 45. Right? Go to the left and find the max value. Right? Then I'll swap them, and delete the max node. Why do I want to delete the max node? Well, because I've already promoted it up here. I need to make sure that that node is not in there because I don't want duplicates. Okay? All right, that seems like a good idea, but does it work? Right? So first of all, how do I find the maximum value? Here's the thing that I want to delete. Now let's call it U. Right? And I'll go to the left subtree here. Right? I need to find the maximum value in this entire subtree over here. Right? So there's a big giant subtree over here. I need to find the maximum value. Do I have to go through a pre-order traversal or an in-order traversal and search absolutely everything here? No. What do I need to do? Well, with this particular example, what did I do? I went to the left tree, and then I went all the way to the right. So in general, what you're going to do is you're going to go right, 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 until you found the maximum value over here. All right? That's still proportional to the depth. We're not looking at everything. Great. But what happens if the maximum value has 2 children? Right? Well, if it has no children, first of all, we know how to deal with that. That's case 1. Right? If it has 1 child, if it has 1 child, we know how to deal with that. Case 2. But what if it has both children? We're right back to where we started. Right? I'm trying to delete a node with 2 children, and now I've just found another node with 2 children. But is that possible? Here's my A and B. Right? Is this really the maximum value here if you have a right child? No, because B is greater than the max by the binary search tree property. So if you just keep going right, going right, going right, that means stop when there's no more right child. Right? We're not going to have enough time to do this, but we are going to complete this today, but we are going to have enough time to at least set us up for next time. Let me get rid of that. As a first step, what I need to do is I need to find the maximum value in the left subtree. So let me go ahead and write another function to do that. I'm not going to make it public because I don't want you mucking around with the binary search tree nodes. Binary tree nodes. Right? And I'll call this getMax. Okay? And I'm going to take a binary tree node, T, and I'll call this U or something. Okay? Now the idea here is that I'm going to pass in the left child, or the right child if you wanted to do the right child instead, but I'm going to pass in the left child, and it's going to go down, down, down all the way to the right until it finds the maximum value. Right? So I need a binary tree node here, T, called current, and I will start at U. Right? While U dot has right child, go to the right child. Current dot is equal to current dot right child. Oops, not parent, but get right child. And this shouldn't be U, this should be current. So all that means is that the current is going to go all the way down to the right until you found the last one, because there is no more right child. And I will return current. There. Okay. Let's set ourselves up for next time here. This is actually going to be the most general case here. If node.numChildren is equal to 2, then we need to take care of this case here. Otherwise, else if. And what I'll do is I'll find that node. So they're both children, so I can just do the left or the right. So what I'll do is I'll find the max, binary tree node T max is equal to, or let's call it max node, so that we're not confusing it with maximum value, is equal to this dot get max of node, right? Dot get left child. So I'm going to go to the left child, and then I'm going to use that function to find the maximum node. Right? Now at this point, I'm going to go ahead and outline the rest of this. Next, step 2, what we're going to do is swap value of max node and node. Right? And then 3, delete the max node from the tree. Actually, we can get this done. Right? This is actually going to be really, really simple. How do I swap out the maximum node and the node? Node dot set value, or set element, to max node dot get element. There. Okay. Now I just need to delete this node right here. Okay. And I know that it has either 0 or 1 child, left or right child, I don't know. Do I have a function to do that? I'm in the function, right? So let's go ahead and try to delete that. This dot delete max node. There. Except it won't work the way that I've designed it. Ah, darn it. What I did is I'm taking the actual value here instead of a node. Well, like I did up here, by redesigning these things to work with nodes instead of actual values, but making it all private, let's do the same thing here. Private, T, delete, and instead of deleting this node here, what I'll do is I'll delete a binary tree node containing that. So what would it be? Node, there we go. And so I now don't have to find it anymore. In fact, we'll do this another, we won't be able to get this done today. But the publicly facing one would be, and let me call this delete node, just to distinguish it. Public T delete node. Oops, sorry, delete TX. There we go. So I'll find it. If it's null, there's nothing to do. Just go ahead and, don't worry about it. Otherwise, this dot delete node, there. And then I will return node dot get element. Now the rest of this stuff I'm going to have to refactor because of course now I've changed the design. But look at, isn't that so much better? Right now down here, what I can do is I can call delete node. Right? And I've already got a function to do that in terms of the node. I'm still going to make this private because I don't want you deleting nodes directly. Instead, you call this function up here. Right? There are a couple more things to refactor, but we'll do that next time. And then, of course, we need to test it. And then we'll get into the last part of the trees and tree discussions, which are going to be heaps. Heaps are another data structure that are based on binary trees. And that's the last data structure that we'll look at for the semester. We still have, 3 days next week and 1 day this week. So we'll probably get done with that kind of earlier, and then we'll have a course retrospective probably on Wednesday, and then we can probably just not have the last course on, or last lecture on that Friday. Because remember, next week is going to be your resubmission opportunity. Details are in Campus Wire. You have to show up. You have to be there. We're also dropping your lowest lab grade, but that'll be next week. And then what's the other thing? Oh yeah, I meant to check, but I don't know what the response rate is. I can give you an update on that Friday. The response rate for the course evaluations, which will feed into another 20 points bonus or something like that. Right? All right, if you haven't been reading Campus Wire, make sure that you're doing it this week. All right, and I'll see you on Friday.